Combustion analysis. One of the common ways of determining the composition of organic compounds is by combustion analysis. A precisely measured mass of the compound is burned in an oven in the presence of oxygen so that the combustion is complete. Since the organic compounds are commonly made of mostly carbon and hydrogen, with oxygen and occasionally other elements, the products of the reaction are CO2 and H2O, and occasionally some other oxide. The apparatus has a furnace in it in which the combustion occurs. The products flow through a chamber with copper-2 oxide, which reacts with the partially burned carbon to complete the combustion if needed. The products of the combustion are captured individually in various materials. Water and carbon dioxide are routinely captured, but other suspected combustion products, oxides of sulfur or nitrogen are common, may also be collected. We weigh the material before and after combustion to obtain the mass of carbon dioxide, from which we can calculate the mass of carbon that burned, and the mass of water, from which we can get the mass of hydrogen that burned. And this information is used to analyze the compound. The big difficulty with this method is that oxygen present in the compound cannot be accounted for from the captured products of the reaction. We need to determine the mass of oxygen in the compound by finding the masses of all the other elements present and subtracting these masses from the mass of the original compound. Let's start with a general reaction for an unknown organic compound containing carbon, hydrogen, and oxygen. When 1 mole of a compound of general formula CmHnOP burns with oxygen, we get m moles of carbon dioxide and n/2 moles of water. For a given mass of the original compound, we measure the masses of the CO2 and the H2O produced. We find the moles of CO2 by dividing the grams of CO2 produced by the molar mass of CO2. We find the moles of water by dividing the mass of H2O produced by the molar mass of H2O. When the carbon compound burns completely, it will produce the same number of moles of CO2 as there are moles of carbon atoms in the original compound, and half as many moles of water as there are moles of hydrogen atoms. So, moles of carbon atoms are the same as the moles of CO2, and moles of hydrogen atoms are 2 times the moles of H2O. To find the moles of oxygen present is more difficult. We need to know the mass of the original sample and the mass of carbon and hydrogen in the sample. Then we find the difference. So we find the mass of carbon by multiplying moles carbon by molar mass, and the mass of hydrogen by multiplying the moles of hydrogen by the molar mass, and subtract each of these from the mass of the original sample. Then we find the moles of oxygen by dividing that mass by the molar mass of oxygen. We then have the moles of all 3 elements and can continue to find the empirical formula and molecular formula in the usual way. Analyses like these were the only way to determine the composition of compounds throughout the 19th century and well into the 20th century. However, today, more modern methods such as mass spectroscopy and atomic absorption spectroscopy that can work with smaller samples and use non-chemical processes are used more commonly. Caproic acid, which is responsible for the foul odor of dirty socks, is composed of carbon, hydrogen, and oxygen atoms. Combustion of a 0.225 gram sample of this compound produces 0.512 grams of carbon dioxide and 0.209 grams of water. What is the empirical formula of caproic acid? First, determine the number of moles of carbon dioxide and water that have been produced. The moles of carbon equals the moles of carbon dioxide, which is the mass of the CO2, 0.512 grams, divided by the molar mass of CO2, 44.0095 grams per mole. This equals 0.011,633,8518 moles of carbon. The moles of hydrogen is twice the moles of water. The moles of water is the mass of water, 0.209 grams, divided by the molar mass of water, 18.0153 grams per mole. The moles of water are 0.011,60125 moles, so the moles of hydrogen are 0.0232025 moles. Remember or write down these values as you will need them later. Now determine the number of grams of carbon. Grams equals moles of carbon times molar mass of carbon, which gives us 0.140 grams of carbon when rounded to the correct number of sig figs. Find the number of grams of hydrogen. Grams equals moles of hydrogen times molar mass of hydrogen, which gives us 0.0234 grams of hydrogen, again, when rounded to the correct number of sig figs. Subtract these values from the original mass of the compound. This gives the mass of oxygen in the original sample, 0.062 grams. Determine the moles of oxygen in the original compound from the mass of oxygen. Moles of oxygen equals 0.062 grams divided by 15.9994 grams per mole, which is 0.003875145,318 moles. Now we have the moles of carbon, hydrogen, and oxygen. Divide by the smallest number, which is oxygen, to get the mole ratios. For oxygen, it is 1. For carbon, it is 3.00. And for hydrogen, it is 5.99. These are close enough to whole numbers to round off to 3 carbon, 6 hydrogen, and 1 oxygen. So the empirical formula is C3H6O.